Okay, this is Chapter 3 for AP Chemistry. This one covers Section 3 and 4, the mole and molar masses. The mole. Because atoms are so very tiny and they are really hard to count, the scientists had to come up with a different method of counting them. So they're counted in groups, like donuts and sheets of paper and pencils. For example, if I told you I had a dozen donuts, you'd know that there are 12 donuts in the box. If I told you I had a ream of paper, then you would assume there are 500 sheets. If I had a gross of pencils, you would assume there are 144 pencils in my gross. The mole is the number of atoms in exactly 12 grams of pure carbon-12 isotope. Remember, you could have also written the isotope identity like this. Experimentally, scientists determined this group to represent 1 mole is going to be 6.022 times 10 to the 23rd atoms in it. That is Avogadro's number. 1 mole of any substance of any kind will contain 6.022 times 10 to the 23rd particles of that substance. How big is the mole? A mole of hockey pucks would have the same mass as the moon. With a little mathematical computation, that turns out to be 1.62 times 10 to the 23rd pounds. A mole of donut holes would cover the surface of the earth 5 miles deep. A mole of $1 bills spending $1 million per second would take 19 million years to spend it. A mole of Big Macs placed next to each other will circle the earth 2.1 times 10 to the 15 times. And the one I love is if we have a mole of days. How many years is that? So there are 6.022 times 10 to the 23rd days in 1 mole. And we'll use the 365 days in a year, disregarding leap year and the 0.25. In 1 year, that comes out to be 1.65 times 10 to the 21 years. So if you had a mole of days, it would take you 1.65 times 10 to the 21 years to live them 1 day at a time. Molar mass. What is it? The mass of 1 mole of any substance in grams. Use the terminology to your benefit. Molar mass is the mass of a mole, a single 1 mole. The units for molar mass are grams per mole, abbreviated G per mole, or you could always say grams per 1 mole. And what's going to be different for everything will be the numerical value that goes there. Every substance will have a unique molar mass. So here's a short example, a very simple molar mass problem. Isopentyl acetate, the molar mass of isopentyl acetate. We are going to figure out 1 mole. So we have 7 carbons. We have 14 hydrogens. And we have 2 oxygens. Off the periodic table, I got the mass, the molar mass of each element in the compound. Executive decision, all the masses that we ever get off the periodic table or use are going to end 2 digits right of the decimal, and we just do our computation here and add them up. Now I'm doing a little fudging with sig figs, especially for this guy right here, because technically he should be 3, but again, 2 digits right of the decimal, whether you're taking it off a periodic table or writing it down as the molar mass of a compound or whatever. So what we've just calculated is the fact that 1 mole of the isopentyl acetate is equivalent to 130.21 grams, or the isopentyl acetate, has a molar mass of 130.21 grams per 1 mole. Notice that it looks like a conversion factor. What I want you to realize too is 1 molecule of the isopentyl acetate, and it's called a molecule because it's a compound, it's a molecular compound, will be equal to 130.21 AMUs, and if you have 6.022 times 10 to the 23rd molecules of isopentyl acetate, and you can't abbreviate molecules, it's already used for the mole, then that's going to be 130.21 grams. Okay, we're going to do another simple mole problem. We're going to calculate the number of atoms in 5.68 milligrams of silicon, and then we're going to calculate the number of molecules in the same mass of water. So silicon first. 5.68 milligrams of elemental silicon. Convert it, unit conversions for the metric system, to grams first because molar mass is in grams, not milligrams. From the periodic table, it says that 1 mole of elemental silicon will be 28.09 grams. And my last ratio will be Avogadro's number, if I can squeeze it in. Going to write really small. Atoms, because it's an element, is 1 mole. Multiply the top, divide by the product of the bottom, and you will find that there will be 1.22 times 10 to the 20 atoms, because it's an element, those are the smallest tiny pieces in an element, of silicon in 5.68 milligrams. Now we're going to do the same thing with water. Milligrams of water. We have to start it out exactly the same. You have to have it in grams because the definition of molar mass is grams per mole. Metric system conversion, 1 gram is 1,000 milligrams. Now this is going to be slightly different. First off, 1 mole, but it's 1 mole of water, which is a molecular compound, not an element, and it has a different molar mass than silicon because it's a completely different substance. Now, 6.022 times 10 to the 23rd is the same numerical value, but the smallest single unit in water is called a molecule, not an atom. And that's 1 mole of water. So notice that they're almost identical with the exception of that ratio right there and the term for the single smallest unit. And you do the math here and you get 1.90 times 10 to the 20th molecules of water in 5.68 milligrams. Alright, a harder mole problem. How many hydrogen atoms are in 145 grams of glucose? This is not table sugar, this is your biological glucose. Okay, so we start with the number given to us in the problem, 145 grams. I'm going to abbreviate the compound as CHO. From mass, using molar mass to moles of, 1 mole of the compound, 6 carbons, 12 hydrogens, 6 oxygens is 180.20 grams. I'm in moles of. This ratio converts me from mass to moles of. Notice this number here, if you're using molar mass, will always be the number 1, because that's the definition of molar mass, the mass of 1 mole. Then 6.022 times 10 to the 23rd single smallest pieces in this compound are called molecules. because it is a molecular compound, not an ionic, and it's not an element, and that's 1 mole. Now, if I stopped here at this ratio, I would be able to tell you how many molecules of glucose I have in 145 grams. It's not what the question's asking. So I have to go one more step. My next ratio has to equate the number of hydrogen atoms to 1 molecule of the compound. And if you look at the formula on the previous slide, there are 12 hydrogen atoms in 1 molecule of the compound. So multiply the top, divide by the bottom. 5.815 times 10 to the 24th atoms of hydrogen in 145 grams of the compound. Alright, another mole problem. This one's going to be just a little tougher than the last. A sample of rhenium-187 contains a certain number of neutrons. Assume the sample is pure rhenium-187. The atomic mass of rhenium-187 is 186.96 AMUs, and we are going to determine the mass of the sample in grams. Alright, so the first thing we're going to do is start with the number given in the problem, 3.613 times 10 to the 24th, and that's neutrons. And rhenium-187. So what I'm doing here is I'm doing a journey. I have to come out of the super sub-microscopic world of neutrons into the macroscopic world of grams. So the first thing I really have to figure out for this ratio is how many neutrons are in 1 atom of rhenium-187. So down here a little bit, let's do a little review here. Your mass number, if you recall, the mass number is the number of protons plus neutrons. The mass number is 187. The number of protons, we don't do nuclear science at all in AP chemistry, so the number of protons we're never going to mess with. The number of protons, according to the periodic table, is 75. Therefore, the number of neutrons for this particular isotope is 112. So there are 112 neutrons in 1 atom, mind you, of the rhenium-187. Alright, so that's going in. I got to keep my journey. I'm going from the super submicroscopic world of the neutron. I got to keep moving on. 1 mole of rhenium-187 will have 6.022 times 10 to the 23rd atoms. They're called atoms because this is an element. It's an isotope of an element, but it's still an element. And then my last and final ratio will be the fact that there are 186.96 grams of rhenium-187 for every 1 mole of rhenium-187. Do the math and you get 10.02 grams of rhenium-187 contain 3.613 times 10 to the 24th neutrons.